You know, everything around us, from the phone in your hand to the bridges you drive across, we build them all hoping they'll never break. But what if we could actually move beyond just hope? What if we could use artificial intelligence to design materials that are, for all practical purposes, unbreakable? Well, today, we're going to dive into how AI is making that future a reality.
I mean, this is the question, right? It's the puzzle that has kept engineers and builders up at night for centuries. It's this constant quest for perfect reliability, making sure our creations can handle whatever life throws at them. And right now, the answer to that ancient question is changing, and it's changing fast.
For the longest time, we've relied on the old ways. You'd run a few physical tests, crunch the numbers, which took forever, and then, just to be on the safe side, you'd over-engineer it. You'd make it way stronger and heavier than it probably needed to be. It's that classic better safe than sorry approach. But AI, it's offering something totally different. We're talking about using massive, and I mean massive, amounts of data to get instant predictions. This allows us to create designs that are perfectly optimized, not just strong, but efficient too.
So the term we're really focusing on here is structural reliability. It's basically the scientific promise that something won't fail. And getting a handle on this is super important because we're about to see how AI is completely rewriting the rules for how we make that promise.
Okay, so how in the world does AI actually do this? Well, you can think of it like a digital material scientist. It's learning to spot the tiny, hidden signs of failure long before they turn into a catastrophic break.
Now, it's really important to get this straight. AI isn't just tossing out centuries of physics and mechanics. Not at all. It's building on top of that foundation. It's more like a powerful partnership, a synergy, where AI gives our classic understanding of materials a massive boost.
In principle, the process is actually pretty straightforward. First, you feed the AI a giant diet of data. I'm talking everything from real-time sensor feeds to microscopic images of a material's guts. Then, the AI does its thing. It finds patterns that a human could spend a lifetime looking for, connecting the dots between stress, corrosion, and tiny internal flaws. And the result? It can predict the breaking point with unbelievable accuracy.
And really, this gets to the heart of it all, the data. The better and more varied the data you feed these AI models, the smarter they get. We're talking about mashing up lab results with data from sensors out in the real world, and even information about how things like corrosion affect materials over time. It's this whole mix that gives these models their predictive superpowers.
This quote from the research really just nails it. This marks the convergence of materials science with data science, powered by machine learning. It's not just an improvement, it's a whole new way of thinking.
But, and this is a big but, this is not a solved problem, not by a long shot. This is where the story gets really interesting, because the real world is infinitely messier than a controlled lab environment, and that messiness creates some huge, unsolved puzzles.
So yeah, this is the question that keeps researchers awake at night. How do you possibly account for all the chaotic, unpredictable stresses that a material is going to face over, say, 50 years of use?
And here's the bottom line. While AI is fantastic at predicting failure under simple, clean lab conditions, it still has a hard time with the messy stuff. Things like long-term metal fatigue, the wear and tear from millions and millions of cycles of stress, or when forces are pulling on something from all different directions at once.
And wow, this chart right here, it just lays the problem bare. Research shows that a material's strength can be overestimated by as much as 39% when you go from a simple lab test to the kind of complex stresses it faces in the real world. That is a massive gap in our understanding, and it's a gap that we desperately need AI to help us close.
So, to close that gap, this is what researchers are really zeroing in on. They're trying to build models that can finally get a handle on long-term fatigue, untangle all those complex stress interactions, and do a much better job of factoring in those tiny internal flaws and the effects of the environment.
But look, solving these puzzles isn't just some academic exercise. The payoff here is absolutely enormous. We're talking about engineering a future with materials that today we can only dream about. If we can crack this code, the result is nothing short of a smarter, safer, and way more efficient world, all built on a foundation of materials that are truly next generation.
Just imagine this for a second. Using AI to discover the perfect recipe for a new metal alloy. For decades, engineers have been stuck with this frustrating trade-off. You make a material stronger, but it usually gets more brittle or more likely to rust. AI can sift through millions of possibilities to find that perfect sweet spot, creating something that's both incredibly strong and incredibly resilient.
Or what about 3D printing? We can already print some pretty complex stuff, but AI could let us design and print what are called metamaterials. These are structures with internal geometries that are specifically engineered for amazing strength at just a fraction of the weight. This is a total game changer for industries like aerospace or even for medical implants.
And all of this leads to a huge shift in how we think about design. We can finally move away from that old conservative model of just over-engineering everything and move toward what's called performance-based design, where every single part is exactly as strong and as light as it needs to be. No more waste. Just pure, data-driven efficiency.
Okay, this all sounds pretty amazing, I know. But before we get carried away and start building AI-designed cities, we have to pump the brakes and talk about some major hurdles that are still standing in the way.
On one hand, you've got this incredible potential for safety and efficiency. But on the other hand, you've got some very real problems. I mean, can we really trust a black box AI to design a bridge that thousands of people use every day? And where are we going to get enough high-quality data to train these models for every possible situation? And how do we standardize all this so that an AI-approved material in one country means the same thing everywhere else?
And this brings us to what might be the single most important takeaway here. The future isn't about just handing the keys over to the machines. It has to be a hybrid approach. It's a partnership where you combine the incredible predictive power of AI with the physical models we know and trust, and, most importantly, with the expertise and oversight of human engineers.
So, as we're standing right here on the edge of this revolution in how we build things, the real question isn't if AI is going to build our world, but how we're going to let it. And maybe the bigger question is this: as we design the unbreakable materials of tomorrow, are we ready to place our trust not just in steel or concrete, but in the code that created them?